Ok, c'è qualcuno da casa in teoria, no?
Quando posso iniziare?
The best of my knowledge.
Uno sì. L'ha messo sul testo.
Io la penso che si chiama Braga, questa qui.
La presentazione.
Questa qui.
Ah, Braga. Okay, so I think we can start this session. And the name of the session is Mathematical Methods for Image Processing and Understanding. This session is conducted together with Professor Ivan Gerace, which will be the first speaker of this morning, and Dr. Arianna Cavallini, both from the University of Perugia, as me. I want to thank you for have decided to participate and to speak at this session. And let me say only one thing. We have a kind of agreement with Journal Mathematics that if you want, you can extend your paper, which has already been published in the spring lecture notes, in order to publish it, to submit it to the Journal Mathematics. So of course, the paper must be extended in the sense that in comparison with the one that you submitted here, there should be some new original results. And we invite you to use this opportunity. The Journal Mathematics, as many other journals, require a payment, but we have an agreement for which we do not have to pay nothing. Okay. Okay. So, since the time is strict, I would like to start with Professor Ivan Gerace from the University of Perugia, and he will speak about on xerographic image reconstruction, the segmentation phase. Thank you, Ivan.
So, good morning. I'm going to talk about sonographic image reconstruction. In particular, we focus this talk on the segmentation phase. So, the sonographic technique uses a stone block covered with cheese, and the results are bold and clear line. The producing part of the block make the design. The ingot is applied on the relief. The color are applied using stencil with shape corresponding to the area to be colored. This is a stone and block, and here there is a Antician Sicilian tarot, and this is going to apply on the paper, and this is the black border that the classical English card desk is the most common use in the world, but there are many local card desks that are used for local game, and we are interested to reconstruct the Perugine card desk that has not been printed since the beginning of the century. So it would be interesting to have a new card desk. This is the card desk that we are going to reconstruct. This is produced by Solensio, and qui non funziona. No. Cosa è successo? And this is the cover of this. Here is right. It's right. Tipo Perugia, so it was a Perugina card desk. Si è incrementato la.
Perché toccato, mi sa che
Cosa fare?
Prova con due dita come.
Sì, però io lo controllo. Sì.
Bene, sì, no. Quando mi giro lo sfioro questo va. Allora, so let's analyze the red problem. We have in the image composed of U+1 image, sub-image. The first one contains only black and white color, and the other one contains a single distinct color. And we have to find this partition to perfectly reconstruct our card desk. The image distortion model is very complex. There are a lot of problems as the card affected and so on. And we have to consider many phenomena. As, for example, the one that I'm going to show you now. In this card, you can see here, there is the break of the black border. And we have to reconstruct this here, the red color overcome the black border. And so we have to find, we have to clear here the card desk. Here, for example, here the black border is black. Here we have a lack of a color, and here the green color is overcome the black border. In this case, here the blue color overcome the black border. Here there is lack of color. And here there is some new color that we have to change this color. It's completely random, the model of the distortion of this car. So the last year in the second workshop in mathematical model, mathematical method for image processing understanding, I proposed a method for the reconstruction of this kind of card. In that paper, I divide the technique in 5 phases. In the first phases, we have to defect the images. So we have to restore the original color. Moreover, the image is blurred and there is some noise. So to make this face, we use a reverse technique. After that, there is a second phase where we want to restore the black, the borders that are black. So for this phase, we for the moment we make it manually, and we want to in some way propose a new technique for this phase. And in the third phase, we remove some artifact and we enforce the color homogeneity. Then there is a phase for the black color regularization, because we want that the thickness of the border are constant. We have to minimize the length of this border. So we here propose another regularization technique. And then, since we change the border, there is some color that are not defined. So we have to find the color of this color that are not defined. Now, we want to introduce a phase for the segmentation of the image. And this phase will be between the first and the second. So it's here in the middle. By this phase, we reinforce the color homogeneity. So in this case, the third phase will be directed, and a new phase will be inserted here in the middle. So to do that, we want to use a color space that is uniform. A uniform color space is a color space that colors that are similar to the human eyes are closer in this space. For example, a uniform color space is the lamp, but the RGB is not a uniform color space. And we use these spaces Q, T, L, C, R star, G star. That is the one that I proposed in the first conference, in the first workshop on mathematical method for image processing understanding. And this is the meaning: quadratic transformed luminous, chrominous, R star, G star space. The name is strange because in that paper we proposed three different uniform space, and we check the property of this space, and we choose that one as the best one. So the name is a little bit strange. And given a color in the RGB space, we obtain the luminance by this formula. And this is the, for the moment, the chrominance coordinate. Then, L is the luminance. To obtain the new chrominance coordinate, we use this formula. By this formula, we have that in the center, in the origin of in the space, there is the white or the black, the green. In some way, this is like a cylinder in the X in this X there is the luminance, and in the other part is the chrominance. In the center of the cylinder there is green, the green up the white, down the black, and the center the green. And here we can notice that this is quadratic in the sense that this is a quadratic term. So it's very simple to find a transformation between the RGB space and the space. So, for example, this is a king of coins. This is from Piacentine desk, and this is full figure. Now the Piacentine has the double figure. This is the old Piacentine one. This is the luminance. That one is the chrominance. This is the alpha components, and this is the beta components. So, to find the true color of the image, we have to work on the chrominance instead of the luminance. The luminance gives the difference, the variation of the color, but the color is given by the chrominance component. So this is what I said before, and this is a section of the chrominance with the luminance. Here the luminance is 118. Here in the center, there is a green, and here there is the other color. What we want to do? We want to find the chrominance of the U plus 1 sub-image. So we look at the frequency of each chrominance component. We take the best one. The best one, the first one, it's sure the one in the center for black and white, because the curve is black and white. It's mainly white, yes. And then, starting from this area, we want to find an area where the frequency of the chrominance is high and is close to this area. And we want to give to all these chrominance the same color, it's the white of the time. Then we have to find the best one, the chrominance that has the highest frequency. For example, this one, so we find in yellow, and we want to find a close area where there is a lot of chrominance with high frequency, and give to this to all this area the same color. Then we find another red and make the same computation, and then we find another blue and make the same computation. Okay, so we want to partition this session in, for example, 1, 2, 3, 4 color, and give this 4 color to our camera. Then, given an image x1, that is the effect of the image obtained by the first phase. Here is the L is the luminance component, A and B are the component alpha and beta respectively. First, we discretize our chrominance component in a grid with a fixed step H. Then we compute the number of occurrence of the chrominance component alpha beta, and with the M function. Then what we want to do, what I said before, we want to divide the chrominance map into U plus 1 area associated with high frequency chrominance that are almost connected. Then we assume that the first one is the one with coordinate alpha and beta equal to 0. That are the one with the color black and white and sun gray. So that the problem is that if we here we start from this point and we look if there are in this area some chromiums with high frequency, and we say we find the force block. But if we don't limitate this area is connected with the yellow, the red, and the blue. So we have to limitate this area. When we have limited this area, the yellow one is not connected with the red one and the blue one. So we can go. But in the first step, we have to limit the area where we have to work. So we create a rectangular area in the chromatic map centered at alpha and beta were at 0, and we try to find the high frequency chromiums that are connected with chromiums 0, 0. If we don't limit this area, we find all the map is connected in some way. So we have to limit this area. So we compute this procedure. The first procedure is about to find the area where the peaks are white or black. Here we have we fixed the value of alpha and beta to the 0 areas. It means that they are undefined for the first moment. In this part, in the rectangle alpha tilde, alpha bar, and beta tilde, beta bar, we fix the value of this value equal to 1. Then to the chrominance component 0, 0, we give the value 2. That is the 2 means that this area is the one that is black or white. Here, this means that we want to scan this area in all direction with the step can be positive or negative. So we scan this area. If the frequency of the component is high and the distance between another pixel marked with 2 and the pixel that we are analyzing here is small, and the value of this area is still not determined, we put this the chrominance coordinate equal to 2. So it's the one that is white or black.
Even. Tempo sta finito, quasi finito, no?
Sì.
Quindi cerca di...
Allora, then with the standard procedure, we find the coordinate that has the maximum value that are not determined. We fix this value to a new color. Then this is the occurrence of the luminance coordinate and with this value, and we to this area we give this value. Alpha is equal to the one that we have determined here. Beta is the same, and L is the maximum of the occurrence of this vector. And then here we make the same thing that we did before. We find all the pixels that are close to this color and have the same characteristic that we see before. Then when we scan all the image, if the alpha EJ, beta EJ is colored, we give the color that we find before. If it's colored by black and white, the alpha and beta component are 0. If the luminance is high, we give the value white. If it's lower than a threshold, we give the value 0. And then we this is for the pixels that are in the in the rectangle that are indeterminate. We give to them the value -1, and then for the other pixel, we fix the value of the pixel with the mode of the pixel around them that are determined. That for the experimental result, I show the experiment
Very short. Because
an experimental result we can not use quantity evaluation because we don't know the original image. So this is the experimental result. This is the segmentation of the area. This is another experimental result, segmentation of the area. This is another segmentation of the area. To show the difference, we show the difference between the segmentation and adenosine algorithm. Here, by the segmentation, we can see that this area is very constructed instead of there. Here, you can notice here, with the adenosine algorithm, we have some other color. Here there is a blended area, and here is a more clear area. For the conclusion, we have to find a mathematical model for the formation problem. We have to make the other phases where the black borders are recovered, and we have to make this algorithm for all the cut together, because shouldn't be difference between the color of one cut and the color of the other cut, and make other reconstruction with other cut desks, for example, this one. Okay.
okay, thanks. Thanks for your talk. Are there any questions or comments? Yes.
I would like to ask, why not use just like standard image clustering for deciding like the colors that compose cards? Because I think that then it could be applied to all cards together. You just take all the pixels along with the colors, you put them in your preferred color space, and then you like image to cluster the colors. What is the advantage of this approach? Okay, means instead.
We have another separate with the
Advantage of this approach from
You to decide the colors that compose the card, we could use k-means, the k-means clustering algorithm in color space. And I would like to know if there is an advantage.
The color. Not me. I choose the color as the part that is most as the more higher frequency in the space. Usually,
it's similar to the k-means algorithm applied in color space.
Actually, yeah.
And can I ask another? Yes, and I think that there are more common color spaces like lab, as you said, HSL. But you choose another case of color space, so I imagine it has some advantages. I think that
it was that if we choose another technique or another color space, there may be difference with the color chosen for the segmentation. So I cannot say which is the best color because we don't know which one is the best one. So it was random. The choose were
Because also you don't have like ground truth, so it's difficult to evaluate which is the best color state.
Yeah.
Thank you, thanks. I have a curiosity. If I have understood well, you do not have ground truth because you cannot have the original playing cards.
Yes.
So how can you estimate your reconstruction without having a ground truth? How?
Then the problem is that if we make an manually original image, we have to choose manually the three codes that we have to find. So if we choose this color, it's not of us the choose of the color of the apple. The main difference will be this. So I can choose randomly the color that I find with my tablet, but I don't know. I think that the only thing it will be going to Genova to the Solesio there is not anymore the acquisition centrale e trovare le 11 che hanno già the color they use for the only solution.
Yes, I understand that you cannot have a pure disposal ground truth, so that's why I asked this. Okay, so thank you very much. Okay, next speaker, Professor Sara Nicoloso from the ICCSA in Rome, and she will speak about the minimum sum coloring problem of circular graphs, CN1Q. Thank you.
Siamo tutti in questo. Eccolo qui. So I'm Sara Nicoloso from ICCSA Rome, and I will talk about the sum coloring problem on circular graphs of CN1. And this is a joint work with my student Eugenio Mediaco. What is a circulant graph? A circulant graph is denoted by CN, A1, AK, and these are called the entries. And in particular, we have that the vertex set is made of n vertices numbered from 0 to n minus 1, and the edge set, oh, I'm sorry, when I exported the file, it doesn't took care of the alignment, so my slides, oh, the font is also different, anyway. and the edge set is made of these edges where a vertex, each vertex Vs is connected to vertex Vs plus aj mod n for each j, which goes from 1 to k. So when k, in particular, we will focus on circulant graph is 2 entries. So when k is equal to 2, we will call them, the entries will be called A and B, and the graph will be denoted by Cn, AB. So we have the vertex Vx is connected to vertex Vx plus A mod n, and this is called an A edge, and Vx is connected also to vertex Vx plus B mod n, and this is called a B edge. We have an example. C12 to 5. So we have the 12 vertices numbered from 0 to 11, and the entry A, which is 2, connects V0 to V2, V1 to V3, V2 to V4, and all the others. The same happens with the entry B, which is 5. It connects V0 to V5, V1 to V6, V2 to V7, and so on. So we get some sort of bike wheel graphs. CNB is connected if and only if the greatest common divisor among N, A, and B is 1. And this allows for defining a special array representation for CNAB. So we saw the array representation, an example, C45, 12, 25. Actually, it is an infinite array. So we have to imagine a matrix. Somewhere we put a 0, and this defines row 0 and column 0. And when we go leftwards, we go adding 12, the A entry. So we put a 12 on the right of the 0. It means that 0 and 12 are connected by NA edge, 12 and 24 are connected by NA edge, and 36 and 3 are connected by NA edge. And here the modulo took part because 36 plus 5 is 48, modulo 45 gives us 3. So in this way we can fill in the entire row. We can go leftwards subtracting A, we can go downwards adding B, or upwards subtracting B, and following this rule we can fill the entire matrix, and we get this. The 0 has been highlighted in green so that you see that the vertices are regularly placed in the matrix. It means that every 12 is on the left, on the right of the 0, every 25 is below a 0, so they are regular bits, and every vertex is represented in infinitely many times on the matrix. So we have n vertices, but we find many copies of the same vertex. And so we define the problem. Now I compare the sum coloring problem with the vertex coloring. The vertex coloring, the classical vertex coloring, consists in given a graph, we want to find a partition, capital V1, capital V2, capital Vk of V, in such a way that, which are called the colors, so this subset are called the colors, in such a way that adjacent vertices receive different colors, and the number of colors used is minimized. Here we have an example, and this graph has been colored with 2 colors, the light gray and the black one, and it uses 2 colors. This is a different coloring of the same graph, which uses 3 colors, so the light gray, the black, and the orange one. And in this case, the minimum is 2. So this is the minimum. This solves at optimality this problem, and this is called the chromatic number. The sum coloring problem is a coloring problem, but it's slightly different from the vertex coloring. And we are given a graph, and we want to find a partition into n subset of V. Some of them can be empty, in such a way that each Vi is an independent set, and this context is exactly the same as asking adjacent vertices to receive different colors. But what is different, what is really different, is the objective function. In this case, we have this objective function. So in some sense, we want to, we have a weight, which is I for color, for the subset Vi. So we want, you can imagine we want to maximize the cardinality of the Vi, which have a small index, because we want to, we have a small weight. So in this case, we have, oh, you see the alignment, however, we have only 2 non-empty subsets. We have 8 vertices, but we only have 2 non-empty subsets. And the cost of this partition, and each of them has cardinality 4, the cost of this partition is 12, because the first 4 vertices have weight 1, and the second 4 vertices have a weight 2. And in that solution, we have this subset, So only 3 of them are non-empty. One contains 6 nodes. Then we have one node black in the V2, and the only orange vertex in V3. And the cost of this is 11. So this is the minimum. This is the optimal solution for this graph, and this is called the chromatic sum of the graph, and this is denoted by sigma of G. Sorry. Why did I study the circulant graph? Because of many nice properties: perfectly symmetric, structurally adaptable, low diameter, they are highly connected, the routing is efficient, they have a uniform node degree and a regular pattern. So they are really a nice way to model local area network data centers. And in particular, if we give an example on the network chip architectures, it means that having low diameter means that the signal low latency. Being highly connected means that they have an increased fault tolerance, because if a node or a connection, an edge fails, then the communication is maintained, and the routing is efficient, so congestion and delays are minimized. And finally, they allow for distribute the traffic in an even way, so that they have been increased performance. And why are we looking to add some coloring on circulant graph? I give you an example. In the post-fabrication testing phase of circulant architectures, the edges of the circulant graph represent pair of cores interfering one another. And the test scheduling problem consists in allocating non-interfering cores, so an independent set, to test rounds. So it means that a test round is a color. Minimizing the number of test rounds, it means that we have a minimum vertex coloring problem on the circulant graph, where each color is a test round. But if you want to minimize the average test lead time by front-loading the scheduling to early rounds, so we want to maximize, in some sense, the cardinality of the colors which have a small weight, this is exactly the minimum sum coloring problem. So let's go back to the model. The main contribution of this talk is that computing, sigma of G, can be done in linear time on the CNABs, but it isn't P-complete on arbitrary graphs, so it means that the complexity, we gave a contribution to the complexity. Actually, in this talk, we will concentrate only on the circulant graphs CN12. And I give you a lower bound for sigma of G for the chromatic sum. We have to recall that any independent set of vertices has cardinality less than or equal to alpha of G, with alpha of G we denote the maximum, the size of a maximum independent set of a graph. So we take our vertices and we look for a maximum independent set. By definition, a graph must have a maximum independent set of size alpha. Then the other independent set, generally speaking, have size less than or equal to alpha. But so we remove it from the graph and we search for another independent set. In the best case, we found an independent set of size alpha again. So we remove it from the graph and we go on performing this step of independent set until we find the last one, which hopefully is a maximum independent set again, and we remove it and we are left with n mod alpha G vertices. So it says that the chromatic sum in the best case, the chromatic sum, it was defined in this way, is follows this formula. And computing alpha isn't P-complete on arbitrary graph, but it is linear-tailed solvable on CNABs. So we are now to the point of computing how to compute alpha. With my colleague Caro Tenuto and Salvatore, we proved that alpha on a CNAB is one half of n minus OCT star, the cardinality of OCT star. But what is OCT? An OCT is a node cycle transversal. It is a subset of vertices whose removal leaves a bipartite graph. So, and OCT star Okay, that means that the graph induced by V minus OCT is bipartite, and OCT star is an OCT with minimum cardinality. And so in order to compute alpha, we have to compute OCT star. And how to compute OCT star? I show you the way in the general case. So we take an arbitrary CNAB. In this case, it is the same as before, C45, 12, 25. And we fix a 0, we choose a 0 with row 0 and column 0. And we want to find a 0, another 0 in the matrix at coordinates R and S in such a way that R plus S is even, and the maximum among the cardinality of R and cardinality of S is minimum. Sorry, the absolute value, because columns are positive if we go on the right of column 0 and negative if we go on the left, and as well as rows, which are positive below row 0 and are negative above row 0. And this is easily done by solving the Diophantine equation, which is RB plus SA congruent to 0 mod n. And in this case, the best 0 is this, whose coordinates are R equal to 3 and S equal to 5. Actually, these coordinates, asking R plus S even means looking for an even cycle in the graph. In fact, 0 is adjacent to 25 with the entry 25, 25 is adjacent to 5, and also the horizontally adjacent to our vertices are connected by an edge, the edge with the value 12. And so we have found an even cycle of the graph, the best even cycle according to this size. And from this, we can derive an OCT star in this way. In some sense, we subtend a chord to this L-shaped cycle in this way. So as far as we know, we can, as far as we can, we go diagonally, and then we perform the other steps horizontally or vertically. It depends on which one is the coordinates of this OCT are 3 and 5, and this size is 5, of course. The nice thing is that, so we can finally focus on the CN12, because on these graphs, the OCT star can be expressed in closed form. And this is the formula. Floor of n over 3 plus n mod 3 is the first coordinate, and the other one is the one you see there. And its cardinality is the maximum among the two, so is floor of n over 3 plus n mod 3. And so alpha, if you recall the formula, can be computed by just following, and it gives us that alpha is floor of n over 3. We need another result, which is we said already that the graph induced by V minus the vertices in OCT star is bipartite, but it is also balanced, and we proved in the same paper. We proved this fact in the same paper. What does balanced means? Means that we have a bipartite graph where the set of vertices is P and R, P and Q, and their cardinality is equal, and it is equal to alpha of G, to the maximum independent set. So when we remove OCT, we already found two maximal independent sets. Actually, another point to focus on is that OCT star, the cardinality of OCT star, well, technically when n mod 3 is different from 0, but in generally speaking, it's okay, is greater than alpha of CN12. And it is greater because, you see, the cardinality of OCT star is floor of n over 3 plus n mod 3, while the cardinality of alpha is n over 3. So this is enough to saying that OCT star, generally speaking, is not an independent set. And so the problem, but it has a nice property, because it can be partitioned into a maximum independent set of this cardinality and the remaining maximum independent set with the remaining vertices. So altogether, we have found 3 maximum independent set and just 0, 1, or 2 vertices, because N mod 3 can take the values 0, 1, or 2 only. So this is an optimal solution because its cost equals the lower bound we showed before. I show you an example on C2312, and so we have, as usual, the 0. The best 0, the best even cycle is given by this 0. So this is the even cycle. So we subtend a chord to get the OCT. So this in gray plus the green 0 is the OCT. And if we remove this OCT from the graph, from the vertex set, we get, so I remove it from the array representation, and we get this one. So I concentrate only on one copy of the vertices, and I show you that you can obtain that they correspond to 2 maximal independent sets. You see the blue vertices are not connected to one another as the yellow ones, and both the yellow and the light blue set have cardinality 7. So we have 2 independent sets right now. And now we introduce our OCT again. And of course, you see that these the vertices which are vertically aligned have a common edge. Every pair of them is connected by an edge. So this is not an independent set, but if we color, if we remove from this set two vertices and color them in red, then we get exactly a maximum independent set in gray plus N mod 3, 23 mod 3, which is 2 red vertices, which are the remaining set. So since alpha is 7, then we get an optimal solution. And I now just put another copy of the OCT just to show you that there are no adjacent vertices with the same color. And there is an upper bound for sigma for the chromatic sum on this graph, and it is a result by Fontaine and Kedusi. And actually, they proved an upper bound for the general CN1Z graphs, sequent graphs. So when t is equal to 2, it means that we have these quantities. It is n over 3 plus 4. And now we have n over 3 plus 9 if n mod 3 equal to 2. And we proved that the chromatic sum, so sigma dg for a sequent graph CN12, has value 6 times floor of n over 3 plus 2 n mod 3. And an optimal solution can be determined in linear time. And so we increase it, improving both on the computational complexity, because the general problem is NP complete, and on the bound above, because we can. So this was what I wanted to tell you.
Thank you very much for your talk. Any question or comments?
That's just one. You approach any kind of characterization?
In which sense characterization?
You know, it's a method, so maybe you can try something.
I'm not sure that all the sequent graphs are Hamiltonian. I'm not really sure. Are you sure?
Yeah, the sequent is
Yes? Well, it depends on the parameters. Depends if it is connected or not. However, no, I did never study the one instance. Okay. Thank you very much.
Any other question? Okay. If not, thank you again.
Thank you.
Okay. Next speaker is Professor Pietro Maurino from the nelle Foglie from the University of Insubria, and he will speak about the smoothing aggregation cascadic multi-level method for image blurring.
Good morning, everyone. I'm Pietro Maurino, and I'm presenting this work, which is a smoothing aggregation cascadic multi-level method for image deblurring. First of all, I would like to thank the organizer of this workshop for having me have this work. This is a work with Marco Donatelli, which is my PhD advisor. And as the title says, we are dealing with the inverse problems, in particular with image deblurring. I'm sure that you all know that the inverse problems are pretty important in math, science, engineering, and essentially the core problem is that we have some observation, we know the model, and we want to know what caused that observation. Classical examples are MRIs, CT scans, image deblurring, blind separation, image reconstruction. But the core problem with inverse problems it is that usually they are imposed. The imposedness, I'm sure that you know the concept, but I want to recall it because I like it, that the imposedness is a characteristic of the problem, which is the negation of the well-posedness defined by Admart. And the well-posedness is essentially the property to have a solution, the solution to be unique, and to be continuously dependent from the initial condition. Well, as I said, usually inverse problems are ill-posed. So let's see a classical image deblurring example in which we have our observed signal B, which has been caused by a true signal X, an image in this case, in which blurring operator A, which is a discretization of a convolutional operator, is applied to our satellite image, and then a Gaussian noise is introduced in the system to perturb the image. Once we have it, we have essentially a linear system, because A is a linear operator, and we can invert it, maybe not algebraically, but using the Moore-Penrose pseudo-inverse, and if we use the standard method, we obtain the disruptive reconstruction, which is by no way usable. As you know, so if we are in this case, so the problem is ill-posed, we have to resort to some sort of regularization. In this work, I will use an iterative regularization. So since we are dealing with a least square solution here, and we want to find the minimum X such that this is true, we try to minimize this problem using some methods such as gradient descent or GGLS or some other optimization method. But the problem is that every time we've got an ill-posed problem with some noise, if we use an optimization method, we have that the reconstruction improves to a such point, and then if we continue to the reconstruction, it is completely lost. We return to this final solution. So in order to make an optimization method an iterative regularization method, we have to impose some stopping criterion. So an optimal time to stop our optimizing. And maybe the most famous one, I am reporting it because then I will recall it later, is the discrepancy principle by Morozov. The discrepancy principle is pretty easy. It prescribes that if we got an estimation of our noise level, we have to stop our iteration when our blurring operator applied to our current reconstruction minus B in norm is less than our noise level, or our estimation of the noise, times a relaxation term that is usually in the application took as 1.01. So essentially 1. And that's all the regularization, iterative regularization part. Now, I would like to introduce you to multigrid methods that are the other ingredient of this talk. Multigrid methods has been introduced way long ago from the studies of PDEs, and the core idea is to have a hierarchy of discretization of our problem, which goes from a fine level in which we have more information, more points, to a coarse level in which we have less information, less points, so a smaller subspace. And we want two operators, two grid transfer operator, R and P. R is a restriction operator, which goes from a fine level to a coarse one, while P is a prolongation operator, I'm sorry, which goes from a coarse level to a fine one. Essentially, this two operator wants to transfer information about our problem to the various level. And the idea is that if I got a problem here, which is hard to solve, once I project it to a coarse level, so it became very small, I can solve it easily, maybe in a more stable way. And these two operators, joined with this grid, grant us the method to pass the information between these levels. Between all the methods, all the algorithm that has been developed in multi-level method, we used a cascadic multi-level approach, which has been introduced in 2010 by Serena Morigi, Lothar Reichel, and Perella Sgallari, which essentially is, it creates a hierarchy of grids, and at the first steps, it computes the restriction of the operator and the right-hand side and the observation. Obviously, we needed to project both our observation and our metrics. Otherwise, we cannot solve it. So once we have restricted our operator and our observation, we start from the lowest level, from the coarsest one, starting from 0. We compute a correction that at the first step is not a correction, is an initial guess through an iterative method. Then we correct it and we redo it. We take our correction computed at the coarse state, we project it to a final one. Then we use an iterative method. They use an iterative method to construct a correction and then correct on the final level. This up until we arrive at the last level, at the final one, and so we have a solution. But one thing is evident. The prolongator restriction operator here and here are not fixed in that algorithm. And usually in imaging, some standard choices are made. A restriction operator is usually an average of a group of 4 pixels that are nearby, 9 pixels that are nearby. Prolongation instead is the transpose of this mean, or Serena Morigi, Lothar Reichel, and Perella Sgallari introduced a more complex prolongation operator, which is based on an edge preservation. We tried to define a data-dependent restriction operator, which is based on a segmentation. And the core idea is that once we have an image, an observed image that has been blurred with noise, we can launch a segmentation. The segmentation gives us essentially the same thing that the a priori choice of a small square of pixel, but with different elements that can be greater, that can be similar. It depends on the choice of the segmentation algorithm that we are using. For example, if we see this toy segmentation, because it's made only by 8 segments, this part is all the black part of the image, the majority of the black part. Here is the other black part. If we use if we use more elements for our segmentation, we can have a restriction operator which better approximate our image. And so maybe it can better preserve the different feature of our image that we want to reconstruct to the coarser level. In order to define this, the steps are pretty easy. We have to notice that any segmentation algorithm is essentially a function of pixels and the element of the segmentation. And this function gives us 1 if a pixel is an element and 0 otherwise. Once we have this function, we can define a matrix. This matrix P is a binary matrix, which essentially has 1 if a pixel belongs to a segment, an element of the segmentation, 0 otherwise. Once we have this P, we have the information on which pixel belongs to which element. And since we want to restrict it, we want to coarsen our information, we want essentially to make a mean. And to make a mean, we multiply this matrix by a diagonal matrix, that lambda, which is defined as 1 over the dimension of each element. So we are averaging our pixel of the image in all segments with their value. A visual example: if we got an observed image, we launch a segmentation. Our restriction operator gives us this as the new points in which we want to compute our result as a coarse level, and in this case, different colors are different values. And then, for computational purpose, we unroll it in a vector form. In this work, we considered only a two-level method, so we are a fine and a coarse level. So we don't have a lot of indexes, just one. And yeah, the question is how to project our metrics, because this is based only on the observed image. To project our metrics, we resort to the Galerkin condition, which are standard in multi-grid approach, which essentially prescribes that the matrix at the coarse level is obtained via the restriction operator multiplied on the right and the transpose of the restriction operator on the left, with the choice so that the part of the left must be the prolongation operator. This formula allows us to project the matrix to the coarse level. But if we choose the prolongation operator as the transpose of this P, we have that every solution that we obtain, when it is prolonged to a final space, will be constant with respect to the edge of every segmentation, because we are solving on a coarse level, and then we project back on the segmentation. So we will have that all the elements that generated that the element in the coarse space will be equal. And it is not a feature that we want in natural images. So to avoid this problem, we applied a smoothing, essentially a smoothing in which, after having prolonged the image, we applied a Gaussian kernel to smooth out the discontinuities, so giving us images that are better resembling natural images. Okay, now the stopping criterion, because if you recall in the algorithm, at every level we had an iterative method. And since we want to go in the direction of a regularization method, we need a stopping criterion. The modes of discrepancy principle was based on an estimation of the noise, but we have an estimation of the noise on the fine level. This does not imply that we have an estimation of the noise at the coarse level. In the original work that I quoted, that I cited, the authors proposed a variant of the discrepancy principle for the correction, so for the case that we are in which C is a constant, which is linked to how much the restriction operator downsampled the image, but they studied only the case for which the restriction operator was an average of 4 nearby pixels, of 9 nearby pixels. And we are dealing with, I can show you another image, regions that are not convex, that can have different sizes. So we have to work to have an estimation. And that's what we did. We essentially defined these average variance norm, which is the mean, the variance for each element of the segmentation. This part here is at course level what it is in its pixel, so it was generated by the mean over the element of the segmentation. So this is essentially a mean of a variance of a mean. And once we have this means of variance of a mean, we can deduce this inequality, a lower bound and an upper bound. In this inequality, n is the number of pixels at the fine level. Yes, fine level. Cardinality of L is the cardinality of element of our segmentation, and the maximum of L and minimum of L are the biggest and the smallest element in our segmentation. So if we want to have a segmentation that has a very big element, we have to consider that one. If one is very small, we have to consider that one. Then, when we assume that the variance at fine level is essentially an estimation of our noise level, we can have these two constants that are linked to this inequality. Mathematically speaking, this only sound one is the same mean, because it's an upper bound. But as we can see here, in this inequality, one is an overshoot, while the other one is an undershoot. So we saw that in the numerical experiment, a choice of C that is the average between two of them gives us good results. Maybe we can over regularize using the upper bound while we are doing too much early stopping using the lower bound, essentially. Now, some images. Okay. Here I'm presenting two tests with some classical test image, different blurring operator, and this different noise level, different segmentation used, and we are using classical performance metrics such as PSNR and SSIM to assess our method. All the implementation of PSNR, SSIM, and the segmentation algorithm that we use are present in the ski image, so standard Python library. The first image is the one that I used for the example, and is 256 times 256 image that has been corrupted by a Gaussian kernel of standard deviation of 5. So pretty high standard deviation, but it's corrupted only with a 0.5% noise level. So very low noise. Here we have the tree image, while here we have the observed one. We use a slick to generate our segmentation, and the segmentation results in 53 elements. So we are passing from a 256 times 256 times 256 times 256 matrix to a 55 by 53, a smaller one. Once we launch our reconstruction method, we can see classical Landweber on the right, or your left, I think, on the A, and our two-level method on the other one. By eye, they are pretty similar, but if we check the performance metrics, we see that the two-level cascadic gives us a better performance metrics. We got at 23.12 against at 33.32 of PSNR and SSIM that are corresponding. This improvement, this slight improvement, is better explained by the evolution of the performance metrics with respect to the iteration number. So we have our two-level method, coarse level, solved, projected to the fine level, and then we use the Landweber up to convergence, not convergence, up to a lot of iteration. And here we can see that the green curve, which is our two-level method, is consistently higher than standard Landweber, is stopped at this iteration, and if we let it go, it would achieve even better performance. And the performance with respect to the PSNR that it attained with our stopping rule are essentially the one that it would have attained using the double of iteration of standard Landweber. Okay, as a second test, we use a variant of classical cameraman, which has been corrupted with a box blur of dimension 6 and 2% noise level, so pretty higher. With respect to the other one, we are not using SLIC to generate the segmentation, but we are using the Senius-Babus algorithm. And the resulting segmentation consists in 126 segments. Here, when we see the two results, we have standard Landweber here and our two-level method here. Just looking at the performance metric, we see that our method attains a 24 PSNR against a 23.880. So a better improvement with respect to the other test. But the thing that I like, if you can see here, there's a line in the reconstructed image that it's not present in the two-level. But in the two-level, since we are using a segmentation, you can spot difficulty by eye some element, that is slightly different. So we are seeing that the segmentation is essentially used in this during the reconstruction process and give us useful information. Another thing that I used to see is that the quote here is more pronounced in the two-level case because we are using a segmentation. So we are using essentially a prior information based on our observation. Same thing with the evolution with respect to time. Here you can see the semi-convergence of the method explicitly. And even in this case, when we stop with our rule, we are consistently higher in the theoretical orbit, and we attain better results. Just to conclude, in the proceeding, there are more tests, one with the GGLS instead of Landweber, so a more optimized optimizer, and a stability result, not a stability result, but a stability study. For SP2 work, could be interesting to go in the direction of a variational regularization at course level, at an affine level. Some methods such as ISTA, so when we are using a prior and not the standard Landweber, could and should be investigated, as well as the use of a full multiplicity framework, so a bicycle, is very interesting, and I'm sure that I find the time to do it. And then the extension to more than two-level, because two-level is easy, but once we have to define what a segmentation of a segmentation is, I have to think about it, to be honest. And here's some reference. And thank you for your kind attention.
Thanks very much for your nice talk. Are there any questions, comments? Anyone?
I want to ask about the CPU time. If it's a two-level method, is an advantage in the actual computational time, because of course the matrix is smaller.
The matrix weight.
So it does feel an advantage, and then I have a question.
Okay, let me go back here. The main bottleneck that we observed is not the segmentation computation, or nor the solution at course level, because that one is pretty instantaneous, but it is the projection right now. To be honest, I'm not a programmer by any means. I'm not a who can program well. So we are not discussing it in the article. In the conclusion, we say this of the overhead, but by CPU time, the most overhead is this part here, this projection.
Because the connected question is that I have a doubt on how you compute the operator at the cost level. You have defined like this one in equation 3. So do you pre-compute this A subset C, or
yeah, we pre-compute it, because you can pre-compute it here if you see the matrix, since it is a cascadic one, you have to arrive at the cursor level and then go up. Since you start from a cursor one, you can pre-compute all the level and then apply them verbatim. So it's all pre-computation. It's all, but the segmentation phase is not as heavy as we thought. In the original paper of Slick and Passion Bubble, there's an explicit time complexity, and is in one case n log n, and in the other one pretty similar. Now I don't remember, to be honest, but I've written them.
Okay. Yes, excellent presentation.
Thank you.
Thank you very much. You published some of those methods in some journals in some, do you have some proposal for project? Because very interesting, because photos and photographs is very important for digital cartography, GIS, remote sensing, something like that. Do you have some opinion to extend these methods?
I want to extend them, to be honest.
Yeah.
This is the first time that I publish a work on this kind of method.
Yeah.
So this is my first multi-grid or multi-level work. And as I said, I want to continue on it, but I don't have any strong opinion right now.
Yes.
I'm sorry.
You're honest. Yeah. Great. Thank you.
Thank you. I have a question concerning the comparison of the methods. You use PSNR and SSIR index. Have you, since I saw that the results are quite similar, even if they are different, have you thought to use some index which is based on the human perception of the image?
I haven't thought about it. To be honest, if I have to make a wild guess, in this case, the one in which we have this line here, and maybe this little part here, I think that something like not SSIM, but the one based on the neural networks. So I can't remember the name right now. So I don't remember.
For example, one is the flip index, but probably
No,
I don't know if you refer to
Flip
this.
I've never used it, to be
It's a
honest.
very recent index.
I've never used it.
Anyway, probably
But okay.
you was thinking to another one.
I was thinking to gradient magnitude
Okay.
GMSD. And for my personal experience, when I use this kind of metrics, these morphological transform result in better indexes. So I think that maybe they can be better index for our reconstruction. I think because we have pretty to no noise in the reconstruction, that there's some, but better than that case.
Yes.
And if we are using a neural network to assess our metrics, not such as the one that I said, but there are some perceptual metrics that essentially use some VGG architecture and extract the weights and compare them. If we use some of them performance metrics, I think that the noise would be a great problem. And since we are essentially removing it a lot, they could be even in that case. But thank you.
Okay, thank you. Okay, if there are no other questions, we thank again the speaker. Next speaker is Professor Ana Mariacu from the University of Sibiu in Romania, and the title is Neural Network and Sampling Cartographic Operator versus Traditional Denoising Techniques. Thank you.
First of all, I would like to thank organizers for giving me the opportunity to attend to this conference. Today, I will present a joint work with Cristiana Alexa, Adriana Travaglini, and Gianluca Vinti. We were interested to use approximation operators, neural network operators, and Sampling-Kantorovich operators in denoising images. We'll compare our algorithms with well-known denoising techniques, and we'll try to show that this new algorithm gives good results. Image denoising is a very important aspect in image processing. High quality of images are very important in many applications as medical images, remote sensing, and scientific visualization. For many images are perturbed by different kind of noises, and here I mention Gaussian noise, Poisson noise, and speckle noise. Most of the classical techniques are designed for special noise, and what we wanted to consider in our work was to obtain a method that can offer a possibility to denoise images perturbated by different kind of noises. So we'll consider the neural network operators and sampling Kantorovich operators. First of all, I will give some I will start with a briefly notion concerning the mathematical tools. We'll start also with some test images that will be used in our experiments. The images are perturbate with these three kinds of noises, Gaussian, Poisson, and speckle. And we use different images which have different characteristics. Our results will be evaluated using the following four metrics in order to compare our results with well-known algorithms. We'll start with a grayscale image, which is represented by these metrics, which the elements represent exact intensity. We associate of these metrics the piecewise constant function, this function, and our denoising image problem will become an approximation problem. So we approximate the image of this function. We approximate this image of this function concerning the neural network operators and sampling Kantorovich operators. Here is the definition of the neural network operators for each point x. The neural network operator gives us average of sample values. Sigma is the kernel which is given by sigmoidal activation functions. And from the definition of the neural network operators, we can see that the reconstructed values is the linear convex combination of the sample values of function f. Sigmoidal function varies uniform between 0 and 1. The density function is defined concerning the sigmoidal activation function, and the multivariate kernel is defined as a tensor product of one-dimension density function. Kantorovich operators, we saw that neural network operators is defined concerning the values of function f, sample values. In the case of Kantorovich operators, we have these operators are defined considering the local integral average over a small region. Here I mention some difference between these two operators. For neural network operators, we use sampled values of function f. For Kantorovich, for sampling Kantorovich operator, we use the local integral average. In the case of neural network operator, we'll have the kernel, which are defined using a sigmoidal function. And for Kantorovich, sampling Kantorovich operators, we use the kernel, which is a function which verifies certain properties. I will not mention in this presentation. I will not come in more details. Sampling density, it's controlled by parameter n in the case of neural network operators. And the parameter W from the definition of sampling Kantorovich operator can control the smoothing. In our experiment, consider these three images: Autumn, Cameraman, Lena, Moon, and Onion. We choose these images because they offer different kinds of characteristics. And we'll consider three type of noises: Gaussian, Poisson, and speckled. And in the right part, we have an example for Lena images, the original image and the images with corrupted with these three kinds of noises. First of all, we were interested to obtain optimal parameters from neural network operators and sampling Kantorovich operators. So for neural network operators, we start with 6 activation functions: hyperbolic tangent, logistic, ramp, and B-spline of order 2, 3, and 4, and give different values for the parameter n. For sampling Kantorovich operators, we consider Jackson kernel and different values of the parameter W. In order to compare the results, we use this for matrices. And more exactly, we consider index mean, that it's the average of these indexes. It is known that the better results are obtained when second and last indexes are lower. So in our mean, we'll instead of these indexes, we'll consider these two quantities. So the optimal parameters have to maximize the index mean. And here we have the optimal parameters for these two operators. We can see that for sampling Kantorovich operators, the parameter W depend on the noises that we use. For the neural network operator, the parameter N, we obtain good results for small values of the parameter N. We have here values between 1 and 3. And on the last column, we have the activation functions. So the best results are obtained if you use logistic activation function. In our experiment, we start with these three images, cameraman, Lena, and Mood, because they offer, for example, cameraman sharp edges. For Lena, we have smooth regions, and for Mood, we have natural textures. What we want in our experiments is to compare our algorithms with the well-known denoising technique. And for each type of noise, we use this noise algorithm. For Gaussian noise, we use this for five algorithms, and Poisson noise we have, we consider this for denoising methods, and for speckle noise we have this for denoising method. And here we have the results. On the first column we have the original images. And on the last two columns, we have the results for using algorithms based on neural network operators and sampling Kantorovich operators. And from these visual results, we can see that neural network and sampling Kantorovich operators give good results. Poisson noise. Here, this problem is a little bit more difficult because this noise depends on the intensity of pixels. And from this picture, we can see that our algorithm performs. Also, in this case, we have the images of on the last two columns. We have the images obtained through the neural network operators and sampling Kantorovich operators. And here we have another for denoising method and results concerning of this method. And the last experiment is concerning speckle noise. This is a multiplicative noise, and from this visual results, we can see that also these two operators perform in denoising images. In order to compare the results, as I mentioned before, we use this for indexes. The first index gives us information about the structure's similarity. The second offers information concerning the pixel-wise error. Third gives us information concerning feature similarity. And the last flip index gives information related to perceptual error. The first and the third index are the values for the first and third index are better for higher values, and for the second and flip index, good results are given for lower values of them. And here we have the quantitative results concerning Gaussian noise. If you look at the bottom image, we can see that for neural network and the sampling Kantorovich algorithm, we have highest values compared with other techniques. For the second index for neural network and sampling Kantorovich techniques, we have the lowest values. For example, for flip, also for neural network and sampling Kantorovich operator, we have the smaller values compared with other methods. So for Gaussian for images corrupted with Gaussian noise, neural network operators and sampling Kantorovich operators offers us good results. And here we have also the error map related to the images corrupted with Gaussian noise. We can see that results are very good. For the cameraman and Lena images, the neural network operator performs better than sampling Kantorovich, and for Moon sampling Kantorovich performs better. But in the case of Gaussian noise, these two algorithms based on approximation operators gave good results. Okay, here is I summarize the previous results. We saw that Simpson FSIM values are highest compared with other techniques concerning the denoising images, and RMSA and flip are lowest values compared with other techniques. So in this case, neural network and sampling Kantorovich operators provide the best overall performance. In the case of Poisson and speckle noise, we will make the same similar experiment. But in these two cases, neural network and sampling Kantorovich operators are not the best, but they are the second best methods. The best results are obtained using VST plus NLM denoising method. And for the moon image, sampling Kantorovich achieves the best of performance. And in the case of speckle noise, Frost and BM3D are the best denoising technique in our experiments. As a final conclusion, neural network operators and sampling Kantorovich operators provide competitive image denoising. And for our future work, we'll be interested to apply this kind of method also in the medical imaging. Thank you for your attention.
Thank you very much for your nice talk. Any questions or comments? Okay.
Thank you. Very beautiful presentation, because I have very interesting for astrophoto. And you said about this method for moon. This method only for moon, not for object outside of the solar system. Because the main problem is in noises of pixels. Because you know that object in space very far away, light years, yes? And it's difficult to catch pixels. What do you think? That this method can be successful or not?
I don't know.
Okay.
I don't have an answer. But it's a good point to our next study.
Yes, thank you so much.
Any other question?
Just out of curiosity. How were the parameter chosen for the numerical test regarding the classical methods such as BM3D and the bilateral filter? They were manually chosen, or there was like an automated estimation in the numerical results, in the experiments?
We use a very classical parameter that usually are considered for this.
Yeah, but how were they chosen? Because in some examples, it seems like they are not optimal. Because if you go back to experimental unit, like there is like this one, the next one, yeah. The next one. Yeah, it seems here like that BM3D is over regularizing.
We test with some of the best parameter.
Okay, so we manually do
test, yes. Okay, other question? Okay, if not, we thanks again. Okay, and next and last speaker of this session morning is Professor Vita Leonessa from the University of Potenza, and she will speak about multivariate generalized gamma type operators, approximation results, and application to image processing. Thanks.
Le cose chiamate sono converse, sono uccelli, ma la richiamo io appena finisco. Grazie.
Okay. First of all, I want to thank the organizers of the conference, in particular of this workshop, for for giving me the opportunity to share with you this recent paper written in collaboration with Arianna Travaglini and Gianluca Vinti, and where we have worked we have proposed a multivariate generalized gamma type operators. We have studied for them some approximation and shape properties, and we dealt also with an application to image processing. In the first part of my talk, I'll give you some details about the theoretical results on this sequence of operators, and then we will pass to see the application to image processing. So just briefly, okay, it's a slide for, I didn't know if there was some engineering or some else. And so we fix some notation, but as usual, RD is the Euclidean space. When we use this ordering, we mean that each component of the vectors satisfies this inequality. The vector Z, null vector is, the symbol for the null vector is this one. For the vector with all components equal to 1 will be is this. When we write this power of a vector to another vector, we use this notation in order to have the product of the singular powers. And if we have this situation, by definition, we set this equal to 1. The set where we work on is R plus D, that is the unbounded interval closed in 0 up to the power D. And what about the function spaces where we work? Essentially, we work with continuous function, real valued functions on R plus D, and C is the classical symbol for this type of continuous this type of functions. CB will be the symbol if we want to have a bounded function. C0 if the functions vanishes at infinity. And further, since we work also on weighted function spaces, later we'll fix a weight. A weight function is a continuous and bounded function, strictly positive, and thanks to a weight, we can consider also some other function spaces for these weighted functions. And both these spaces, all these spaces are Banach spaces with respect to the relevant norm, the sup norm in this case, and the weighted norm in this case. So in order to define our multivariate operator, we fix a vector nu of parameters. Nu is must be have to satisfy these assumptions. So for every n, the Gn nu operator of order n is defined by formula 1, where you can say the gamma function, the special function, and also that the function f is mapped into this this integral over R plus D, where the function here is computed into the Hadamard product between the two vectors. Oh, sorry. It's probably more sensible. Okay. And for the moment, we can think about f as a function such that the integral in the formula is convergent. I want to point out that for the one-dimensional case, so D is equal, when D is equal to 1, we get the following definition, which by a change of very simple change of variable turn into the so-called generalized gamma type operators. These operators have been introduced and studied in this paper by Mirella Cappelletti Montano from the University of Bari, Arianna Travellini, and myself. And the name of these operators is related to the fact that if you look at the kernel of this integral, this is a probability density function related to a gamma process, random process. And I want to point out also that here 0 is not included, but it's not a problem because this definition can be extended to also, that means this function can be extended in 0 because as proved in this paper, the behavior of these operators at 0 but also at infinity is the same of the same that the behavior of the function. So if you have a function that is continuous in 0, you can define these operators as f in 0 and at 0 as f defined in 0. And so we can extend in this way this type of operators. And so we call these multivariate operators as gamma type operators for this reason, but also because these multivariate operators can be viewed as a probabilistic type operators in this sense, that is, as operators associated with a vector of dependent random variables of each of which has a gamma type distribution of this time. So we have the product of these kind of gamma processes here. Such operators are positive, linear, they are well defined on the space of continuous and bounded function of this set, and this inequality between the norms of the original function and the mapped function is false. That is, we can say that there are positive linear and contraction from CB into itself. But this is not the bigger space where we can define on which our operators are well defined. In fact, in this slide, we see another space, a bigger space, that we denoted by E nu. E nu is the space of functions such that condition 6 is satisfied, and in this condition, we see a function H nu defined in this way. This is an integrable function where each one-dimensional function involved here are defined by formula 7. This slide, there is a list of some functions that belongs to this particular space. For example, polynomials are functions on which our operators are well defined, but also exponential function of this type or product where the logarithm is involved. So, in order to prove some properties result, approximation results for our operators, we need some explicit expression of our operators, and we have computed them in this lemma. PRI, as we'll see later, will be very useful in our scheme, are the coordinate functions, the projection of on R plus D. And essentially, we have to remind the last ones, where we see PRI, the square, and in particular, sum of the square of PRI. From this lemma, in particular, the first formula, we can see that our operators fix continuous functions, and also preserve polynomials in the sense that they maps they map polynomials of the total degree m into polynomials of the degree total degree m, but this is not the only shape preserving properties that they share. And in particular, we can see in this proposition that if f is a monotone function, the monotonicity, with respect to each variable, the monotonicity is preserved. The same happens for the convexity, and also for the Lipschitzianity. We have that if we have a function with this Lipschitz constant, then the approximation of f has this Lipschitz constant. Okay, so we fix the weight. We fix the weight in this way. In this way, we need this condition about the weight in order to have that the space of continuous functions, weighted continuous functions, is included in our bigger space well definition of the operators. And then the operators maps this space into itself. Here there are some examples of weights that satisfies this condition, and this condition together the 13 condition again on the weight allow us to see that our operators are continuous operators and maps this space into itself, and the same happens for the other space where the function are vanish to infinity, and we have to compute also the norm, operator norm of these operators in the relevant space. So lemma, proposition, but also a Korovkin's result help us to prove the main theorem, where we can say that under the additional condition that you see here, our operators are an approximation process for this space, a function space. That is, this limit relation holds in the norm of with respect to the norm of this space. And in particular, if we work on CB, we have that this limit relation holds for every uniformly on any compact subset of R plus D. Just a few words about Korovkin's results. They are general results that are useful when you want to prove that a sequence of operators, positive linear operators, is an approximation process, and they are a powerful tool because they allow to obtain this type of formula just by checking it on a set of a finite set of function, the function test. And in this case, the function tests are the projection and the sum of the square of the projection, and also the constant functions. This is the last example of related to these theoretical results, where we can say a polynomial weights that satisfies all the assumptions we made before. So we can pass now to the application. Oh, sorry, there is also a slide where we have considered the test function, a graphical representation of the approximation result. We choose this test function in a two-dimensional case. Here you can see the reconstruction of this function by means of the multivariate general gamma type operators, where we have chosen the vector of parameters in this way. And you can see in this picture the case n equal to 5 and then n equal to 40. For the exact function is represented by the black dashed mesh. Here you can see well. And the colored surface represents the approximation. And together, in order to show you the approximation accuracy, we can see here the table of for the RMSE for some values of n. Okay, so we pass now to the last part of my talk, that is the application to image processing. The goal is the same we have seen before. We have a picture, an image represented by the function of this type, and we want to approximate the want to have an image to reconstruct an image that will be a good image with respect to some metrics. So classical denoising methods such as the following one: Gaussian convolution, bilateral filtering, anisotropic diffusion, and Wiener filter. That is the classical methods we'll use also in the next slides. They perform well in terms of these two matrices, but they don't guarantee preservation qualitative properties such as monotonicity or convexity. And so we propose in our approach our operators as a filter that preserves these type of qualitative properties. We give this definition in the paper that says that if F is an image, satisfies a certain structural constraint C, and we consider the observed image with the noise, epsilon is a noise, then a smoother S is said to be structure preserving with respect to C if it preserves the structural constraint. This is very important in many applications, such as the fact that these properties are preserved is very crucial in several image applications. For example, in hydrological analysis of digital elevation models, or in application in analysis of infrared thermography and aerodynamic pressure mapping, and so on. We needed a new metric in order to measure this type of characteristic of filters, and so we have done this definition, the definition of the monotonicity violation index. So if F is a discrete image that is non-decreasing in the horizontal direction, such that the following conditions are satisfied, for a processed image F tilde, defined on the same domain, this new metric is defined in this way, and this metric measures the preservation of the monotonicity. So if this index is equal to 0, we have that the monotonicity is perfectly preserved. Of course, larger MVI values indicate stronger violations. And so we have compared our operators used as a filter with the classical smoothing methods mentioned before. We have considered just one example in this paper. So we have considered the synthetic monotone ramp image defined in this way. We have perturbed this image with the Gaussian noise with 0 mean and this value for the variance, and we have used our operators with these parameters, both the components of the vector nu is equal to 2 and n is equal to 20. This is slide where we can see the visual and quantitative comparison between these methods together with the table. And this is the original image with the noise, and these are the output obtained by means of the methods, the classical methods mentioned before, and the last one is our method. And so in this table, you can say that, of course, thanks to the shapes and the properties that our operators preserve, we have that the new index is equal to 0. And but we have noted also that these operators perform better also for the other two indices considered here, PSNR and SIM, and metrics, usual metrics that we can consider in this case. This is my last slide. Yes, last slide. I just want to say something words about the possibility to extend this work. In fact, we can consider, for example, other type of noise and foresee what happens, but also as made by Anna and her collaborator, we can, for example, compare our operators with other type of operators used in this case, in this application as a filter, and of course also consider other images. So we can extend our paper. Okay, thank you very much for your time.
Okay, I just read that this paper has a different direction of investigation as Professor Messa said. For example, there are many other operators which has similar shape and certain properties, so we can implement that operator in order to make a comparison. Okay, if there are not any other questions, I thank the speaker. Thank for the speaker for this your nice and interesting presentation. And let me just say that our session will be at 2 o'clock in this room with the last speaker, Professor Giuseppe Scarlato. Okay. Thank you. So for our project, you solved it. This is for the in two applications, one with the legal, one with
Era un po' per fare which translates original signed by you. Yes, yes, for both. Yes, yes. If you find somebody, otherwise you will need by regular page.
that may be the best. I have to meet at the best on the sent to you.
ICCSA.
I said, we are clear the best on the sent to you. I know that the same applies to okay, so now we try to substitute. And I think to both that we succeed. Thinking that make me two contracts for one that is uniform. No, it's because
In your case,
no, because the competition one promises the position that they are already under is enough. But if the contest però c'è due, siamo fatto because I am which is not ready to the standards, but has been already written by supervisor. But I wrote that my activity process. I want to ask if I can go or I can change it.
Sì, dopo alle due, sto facendo un test veloce ora, tolgo dalle scatole.
I will work for this project and yeah, but
Quello dietro piatto, quello piatto
now the bottom problem is the CB. I have to ask yes, but in case I just do
Io avrei bisogno, non sempre spostato, di stampare un documento che è un curriculum e devo firmare in originale. Voi avete la possibilità qui?
Io faccio un disco, diciamo, la
E do il codice base?
bisogna chiedere ai ragazzi, oh, guarda, c'è una, guarda, ti faccio vedere una cosa perché l'ho notata, anche se sono di qua, andando al bagno, ho visto che c'è una cafeteria.